Welcome to your podcast for Lesson 49, Non-Uniform Circular Motion. After watching the podcast, you should be able to describe inertial and non-inertial reference frames, define centrifugal force, and solve problems involving non-uniform circular motion. In the warm-up, you had a 615 kilogram race car completing a lap in 14.3 seconds. The track had a radius of 50 meters. We know the car moves at a constant speed, but we want to find the acceleration of the car. Remember, even though it's going at a constant speed, it's accelerating because it's constantly changing directions as it moves around that circular track. All right, so the equation that we're going to use is A is equal to V squared over R. And we know our R value, it's given to us at 50 meters, but we don't know the velocity. So we have to actually calculate that first. So remember, as that car is going around this circular track, right, the distance that it's traveling is the circumference of that circle. And so I can use my V equals D over T equation and substitute in the expression for circumference, right, which is 2 pi r for my distance divided by t. So 2 times 3.14 times my radius of 50 meters divided by a time of 14.3 seconds. When you plug and chug that, that works out to be 21.96 meters per second. Now that I have this, I can plug this into my centripetal acceleration equation. So 21.96 meters per second, and all of that squared divided by 50. Plug and chug, and this is going to give you 9.65 meters per second squared. So answer number 1. All right, when dealing with circular motion, there's really two different reference frames that you need to be aware of. The first of which is called an inertial reference frame. This is where you can explain observations where Newton's laws hold true. So remember, the first law is the law of inertia. Second law, which relates acceleration to mass and net force to acceleration. And then Newton's third law, where every action has an equal and opposite reaction. So an example of a situation where you have something moving in an inertial reference frame would be watching a car on a racetrack go around on that circular track. We know that it's actually able to turn because of the friction between the tires and the road. So in that case, as it's going around that circle, the friction on the tires is going to be what provides that centripetal force, allowing it to complete those turns. The second type of reference frame is referred to as a non-inertial reference frame. This is where you think you're experiencing a force, but it's really not true. You have this imaginary force that needs to exist for Newton's laws to hold true. And you've probably all experienced this. You're in a car, you're going around a turn, and you feel like you're being pushed towards the outside of the car. You say that this push is from some imaginary force rather than the inertia of your body. But remember, if you're rounding a turn in a car, your body wants to continue moving forward in a straight line, according to Newton's first law. So you're really feeling your body's inertia, but you feel as though some force is pushing you outward. That imaginary force is called centrifugal force. Now, centrifugal means center fleeing. So it's going to be going away from the center of the circle. So the motion of an object is non-uniform when other forces are acting on it besides its centripetal force. So let's pretend that we have a rock, for example, or any object that's moving in a vertical circle. Okay? So let's just draw this object at the very top. Okay? We'll draw it over here on the side. We'll draw it here on the bottom, okay, and over here on the right side as well. Okay. Now, if we start at the top, we know that when it's at the very tippy top of its path, this object is going to be acted upon by gravity, which is straight down. And if I'm whirling this stone or whatever the object may be on a string, it's also going to have a tension That's providing the centripetal force. Okay? But there's an imaginary force acting here, which we refer to as centrifugal force. So we'll just label that FCF. And again, that tension by the rope or the string or the cord is going to provide our centripetal force, which we'll call CP. Okay? If we move down to the bottom of our circle, we know gravity is still going to act straight down, so we've got our FW. Okay? But this time, the tension that's providing the centripetal force is still acting towards the center. So it's opposite. There's a second force, though, that imaginary force that's acting in the same direction as the FW, right? And that is the centripetal force, or centrifugal force, rather. Okay, that imaginary force, that's really the object's inertia. We can do the same thing on the left and right sides of our drawings. We know that gravity is going to be acting straight down. Again, the tension which provides our centripetal force will be acting inward towards the circle. And our centrifugal force, again, fleeing, center fleeing, so it's acting away from the center of the circle. And same thing over here on the right. We know FW would be going straight down. We know it's got a centripetal force provided by the tension on the string, and a centrifugal force, that imaginary force, acting away from the circle. And you could do this at any point on this circle. When we're solving problems that deal with non-uniform circular motion, we're going to make F net 0 and use centrifugal force instead of centripetal. So pretend that you're on this roller coaster that you see in the picture. So the roller coaster car is going to speed down a hill past point A and then roll up a hill past point B. And we're going to start by focusing on point A. The car has a speed of 20 meters per second at point A. And the normal force acting on the car at that point is 20,600 newtons. And we need to solve for the mass of the car. Now notice when you're dealing with non-uniform circular motion that you can draw in this imaginary circle to help you label your centripetal and your centrifugal forces. Okay? So in this case, we know that that roller coaster car is going to have an FW, which acts straight downwards because gravity acts downwards. And we're told that it also has a normal force of 20,600 newtons. Now remember, normal force is the force that acts perpendicular to the contact surface. And so in this case, that normal force of the track is actually providing our centripetal force. We also have an imaginary force, which we now know is centrifugal force, which is acting away from the circle. Now, remembering that our F net needs to be 0, that tells me that my normal force has to be equal to these other two forces, FW and my centrifugal force, which are going in the opposite direction. So Fn is equal to Fw plus FCF. Okay. Now at this point I need to start substituting some things in because I need to be able to solve for mass in this problem. All right, I'm going to keep Fn because it gives me my value of my normal force at 20,600 newtons. And for Fw, I'm going to substitute in mg. And for centrifugal force, I'm going to substitute in my mv squared over r. Okay. At this point, it's just algebra 1 rearranging this equation. So what I'm going to do is I'm going to factor out the mass, which is going to leave me with the quantity of g plus v squared over r. And I need to solve for mass, so I'm going to divide each side by that quantity of g plus v squared over r. So it's going to leave me with normal force divided by g plus v squared over r. So 20,600 divided by, make sure you use parentheses here, the quantity of 10 plus your velocity, which is 20 meters per second squared, divided by your radius, which for the hill here at point A is given to you at 10 meters. And when you plug and chug, you should end up getting 412 kilograms. Part B of this question wants to know the maximum speed that the car can have at point B for the gravitational force to hold it on the track. And so right here at this point, you need to understand that if the acceleration of that car is any more than g, right, that pull from gravity, it's going to fly right off of that track, and you obviously don't want that to happen. And so you can say that A has to equal g, okay, because it wants the maximum speed that that car can be going. Now, I also know for centripetal motion that I can take my equation v squared over r and substitute that in for the acceleration. So set that equal to g, and I'm solving for v. So when I rearrange this, I would have to multiply each side by r and then take the square root. Okay. So v is equal to the square root of 10 times r. In this case, our radius is 15 meters. And when you plug and chug that, you should get 12.25 meters per second. The other way that you can think about this problem is that at point B, we know that it's going to have a force of weight caused by gravity, and it's also going to have this centrifugal force that's acting outwards. And if it's going at its maximum speed, it's really not going to have any normal force at that point. And so another way to solve this problem when you look at this is you could set Fw equal to centrifugal force, and then we can substitute in mg for our Fw, and we can substitute in mv squared over r for our centrifugal force. Masses cancel out, and you're left with exactly the same thing you were over here. So just another way about going about solving this problem. Okay, an example, problem number 1, you have a carnival clown riding a motorcycle down a ramp and around a vertical loop. Okay, so he's going to be going around that loop. If the loop has a radius of 18 meters, what is the slowest speed that the rider can have at the top of that loop to avoid falling? Okay, so again, I'm thinking about this point right at the very, very tippy top, and I need to figure out the slowest speed that that clown can have. Now, very similar to what we just did in the last problem, is you can make the assumption that at that point, A has to be equal to G. If it's any less than G, then gravity is going to take over, and that clown is going to fall straight down. So just like in the last problem, we can substitute in v squared over r is equal to g. Rearrange this equation, and then take the square root. And when you plug and chug, 10 times the radius of 18, take the square root of that, and you should get 13.4 meters per second. Okay. Again, also like the last problem, you could understand that at this point at the very top of the ride, right, Fw has to be equal and opposite to the centrifugal force. Okay. And so once again, you could set Fw equal to the centrifugal force, substitute in our known equations, okay, and you're going to end up with, again, the exact same thing that you did in the first part of our solution. So either way, you can plug and chug, and you're going to end up with this velocity of 13.4 meters per second. Okay, in example number 2, you have a 1.13 kilogram ball swung vertically from a 0.5 meter cord in a circular motion with a speed of 2.4 meters per second. We need to find the tension in the cord at the bottom of the ball's motion. Okay. So if we draw a quick sketch of this, Okay, here's the ball at the very bottom of its path. We know that it's going to experience a pull by gravity, so it's going to give it a weight. We know that what's allowing it to move in that circular path is the centripetal force provided by the tension in the cord. And we also know that it's going to experience this centrifugal force, or center fleeing force, which is going in the same direction in this case as our FW. Now, we know that F net has to be 0 here, so we can set tension equal to FW plus that centrifugal force. Okay, and we can substitute in. We know FW is equal to mg plus centrifugal force, right, which we know is equal to mv squared divided by r. All right, so we know our mass is equal to 1.13 kilograms. We know our value for g is 10 meters per second squared. Okay. We know our velocity is 2.4 meters per second, and we know our radius is 0.5 meters. So when you plug and chug this all out, you should get 24.3 newtons. Okay, in example problem number 3, you've got a mythical warrior swinging a 5.6 kilogram mace on the end of a magically massless 86 centimeter chain in a horizontal circle above his head. Okay, so this time we'll draw our circle this way, okay, so that you can picture it's going in a horizontal circle above his head. The mace makes one full revolution in 1.8 seconds, and we need to find the tension in the chain. Okay. So again, let's just say, for example, that the mace is right here. Okay, here's our center point. We know tension is going to provide that centripetal force. Okay, and we know it's also going to experience a centrifugal force, okay, going away from the center of that circle. Okay. And in this case, we don't really need to worry about the FW because, again, what's causing that net force, what's causing it to accelerate in that circle is the tension in the string here, or in the cord. So first thing that you want to notice is that the chain is given to you in a radius of 86 centimeters. The first thing you want to do is convert. So remember, to convert to meters, you would want to put centimeters on the bottom, and you're going to be dividing by 100, which is going to give you 0.86 meters. Okay, so mass always needs to be in kilograms, and your radius always needs to be in meters. Now that we've got that converted, we can set the tension equal to the centrifugal force, because again, F net has to be 0. And I can substitute in here for my centrifugal force mv squared over r. Now, I was not given a velocity in this particular equation, or in this particular problem, so what I can do is solve for that. Again, remember, as this mace makes its way around this circle, the distance that it's traveling is the circumference of the circle. So when we set v equal to d divided by t, we can substitute in our formula for circumference. So 2 pi r over t. So 2 times 3.14 times 0.86 is going to give us a velocity of 3 meters per second. Now I can plug this into my tension equation. Okay, so I'm going to take my mass of 5.6 kilograms times my velocity of 3 meters per second and square that, divided by my radius of 0.86 meters, and that's going to give me, when I plug and chug, a tension of 58.6 newtons.